My name is David Mayasan Quintana. In this video, I'm going to present my final project titled Acceleration Techniques for Chess Piece Recognition, advised by Alberto del Barrio Garcia and Manuel Prieto Matias. Firstly, I'd like to give you a brief outline of my presentation. We will start by looking at the motivation and goals of this project. We will then proceed to the core of the work, which has been the chessboard detection, piece classification, and the optimizations we have applied. Next, we will look at the results and we will see a short demo. Finally, we will show some future work and end with the conclusions. The recognition of chessboards and chess pieces is very important in order to compete against chess engines using a physical chessboard. It is also essential for chess tournament organizers who want to broadcast the games online, or for amateur players who want to share their games with friends. Therefore, our goals are to construct a fully functional framework which is able to process new images as fast as possible on an embedded system. Its final output should be the FEN notation layout of the board. In order to take the pictures, our proposal is to have a webcam on one side of the board. In this way, each time a player presses the clock, a new photo is taken. This photo will then be analyzed by a Nvidia Jetson Nano platform. In order to completely digitize the layout, we must first detect the chessboard and then proceed to recognize the pieces. Once we have this done, optimizations were made to reduce the overall runtime. Currently, DGT electronic chessboards are used in tournaments to digitize the games. However, they are more expensive than our inference platform. The chessboard detection is done in an iterative manner, as can be seen in the top images, refining the chessboard position over 3 iterations. Each iteration consists in 3 major steps as shown in the pictures at the bottom of the slide. Detecting straight lines, searching for lattice points, that are those that form the grid of the chessboard, and obtaining the chessboard position from these points. Note that the lattice points only wrap up the center 6x6 square of the board, given by the red dots, so you must take a border around it before moving on to the next iteration. The final output of each processed image is a string describing the layout of the board. An example is shown in this slide. Squares are labeled left to right and top to bottom, and each piece is represented by its first letter, except the knight, which is represented by the letter N. Black pieces are written in lowercase, and white pieces in uppercase. The numbers show how many blank squares are there between the pieces. In order to train the neural networks that we have used to classify the pieces, we have joined 2 datasets that add up almost 55,000 photos. These images are obtained by splitting the chessboards into their individual squares. Some examples of how the pieces are split can be seen at the bottom. In order to classify each square, we have trained several convolutional neural networks on the pieces dataset from the previous slide. The 4 networks on the left are more complex, and the 4 on the right are faster models. This way, we were able to check their performances, as we will see later, and choose the best ones. Their output is a probability vector indicating to which of the 13 classes does the image belong. In this example, there is a 77% chance of it being a black rook, and a 22% chance of being a black bishop. Once we have the probability vector of each square, we must decide the final board layout. In order to do this, we introduce domain knowledge into the decision making, thus limiting, for example, the maximum number of pawns per player. The order in which we process each square is given by the highest probability for each of the pieces. Optimizing the overall runtime was the next step of the process. Firstly, we have reduced the inference time of the neural networks that we have used by transforming the models to the ONNX format. Once standardized, we can optimize their execution using the ONNX runtime or apply further enhancements by means of the TensorRT optimizer, which we can then execute efficiently on our platform. In this manner, we reduce greatly the inference times by taking advantage of the accelerator available, namely the GPU. When detecting the chessboard, we have applied a series of optimizations with which we have increased the speed by a factor of 4, thus reducing the time from over 16 seconds to just under 4 seconds. First of all, when deciding if a point of the image belongs to the chessboard grid, in certain simple cases a geometric detector is enough, but in some more complex situations, a neural network is needed. We have optimized the neural network that is employed in this case by executing the inference using ONNX, as we have seen before. Secondly, we have reduced the overhead caused by some calls to the NumPy library in two-dimension calculations. An efficient way of computing the intersections of a large set of lines is the Bentley-Ottman algorithm. However, in situations in which there are few lines, it is actually faster to brute force the search. Finally, we have applied a series of minor optimizations to the whole detection process, achieving the results shown in the slide. Here we can see the accuracies that we have reached using the different CNN models. Instead of simply using the top 1 value, we have gained between 1 and 4% accuracy by adding domain information to the probability vectors, as we have seen earlier. Optimizing the execution of these models on the Jetson Nano board using TensorRT has meant a speed increase by a factor of between 2.8 and 6.5. We compute the whole board in one batch of 64 images, and as this way, the optimizer can use the resources available in the platform more efficiently. By plotting the execution time and the accuracy achieved by each model, we can choose the ones that optimize these values, given by the Pareto front in orange. In this case, we would choose SqueezeNet or MobileNet with alpha 0.5 if we want a faster execution, or exception for a more accurate result. In this table, we summarize the times required by each of the phases of our program. In the end, using the faster models that we have mentioned before, we achieved a total time under 5 seconds per new chessboard. In the cases in which the board and the camera stay still, we can avoid the chessboard detection and achieve faster times. In these situations, we can process a full image in under 1 second. In this demo, we will show one of the tests used to measure the results of our framework. On the console, we will see the outputs of 5 different chessboards. These outputs include the elapsed times for each of the steps and the final FEN string. We also measure its accuracy against the real layout. We can check the results of the first test by viewing the predictions on a chess editor and comparing with the input image. Note that all of the locations of the pieces and their colors have been predicted correctly. As we have seen in the video, currently the output of our program is simply a FEN string, and the interaction is made fully on a console. Thus, there is much room for improvement in the usability of the framework. Nowadays, some high-end smartphones include potent GPUs. In addition to the platform we have used, optimizations could be made to include these devices to our framework, therefore making it even easier to deploy. When splitting the individual squares, we have followed the naive approach used in the datasets that we have managed to find. This approach simply splits the final image of the board detection into an 8x8 grid, but this has some major issues. I would like you to look at the selected square. Due to the perspective of the photo, only the base of the white piece can be seen. In order to see the whole piece, we must go back to the original image and work out the positions of the corners of the squares. Once we have this done, we can then see the full length of the piece. We have introduced a new way of splitting individual squares. In these images, a comparison is made between the naive way in green and our proposal in yellow, which takes into account the height of the square. Unfortunately, due to the current circumstances, we were not able to create an image dataset following our proposal, so we had to follow the naive approach, as we mentioned earlier. Implementing our idea could improve significantly the accuracy when classifying the pieces. To sum up, we have built a fully functional framework that is optimized on an embedded system, the Nvidia Jetson Nano, achieving 95% accuracy when detecting the chessboard and between 91 and 94% accuracy when classifying the pieces. Optimizing the different phases of the program, we have sped up the chessboard detection by a factor of 4, and the piece classification by a factor between 2.8 and 6.5, depending on the model used. Overall, we have achieved an execution time that can keep up with a live chess game. We can process a new chessboard in under 5 seconds, and subsequent boards in under 1 second. The full source code is available open source at our GitHub. Thank you for your attention.